Howdy everyone, today I'm going to show you the workflow how to get the heat transfer coefficient in SimLab. Here's the problem description. We have an elbow with two inlets. The main inlet of 1 meter per second as inlet velocity at 350 Kelvin, and the second smaller inlet at 2 meter per second at 298 Kelvin. We maintain a constant temperature of 600 Kelvin at the outer wall. Air will be using as a working fluid, and the final goal is to solve for the heat transfer coefficient with the user determined reference temperature. So the final result we want is to look something like this. Let's go ahead and head into SimLab. I will start by importing the geometry and then mesh it first before I set up the simulation. We can importing the geometry by just simply drag the Parasolid file and drop it in here. And let's play some surface, some regional mesh control. So I want to refining the mesh over here where the mixing happening. So I'll choose a cylinder. And we'll adjust the refinement region so that it can refine at the desired region. Click OK. Put this as 2. 45 degrees fine. Select this body. Surface mesh. The mesh looks good to me, and then I'll with the regional refinements, and it's expressing on the surface level, and I'll go ahead and volume mesh it. And now we ignore the boundary condition on the symmetry plane, the outlet, and the two inlets. Fraction of the mesh size, I can do 0.2 with 4 layers in total. Grow rate is 1.3, which is fine. The average element size I'll choose at 4 millimeters, which is the same as my surface mesh sizes. Okay, the mesh is done. So I'll go to the next step, which is about setting up the simulation. Go to Solution, Flow, choose this body. When we want to get the heat transfer coefficient, the most important thing is to enable the derived quantity output, which will write out some turbulent properties of the flow. And in order to do that, we can go to Result Request, Derived Quantity Output. We change the output frequency to 1. And then in order to get the solver to solve the problem faster, I can choose a number of processors to 28. It will be depends on your computer. So the problem description, we have two inlets. We have the smaller one at 2 meters per second and the main one at 1 meter per second. And the smaller one has 298 Kelvin and the main inlet is 350 Kelvin. Go ahead and rename it. So we want it to be in meter. We can go ahead and change the unit. This will be 2 meters per second at 298 Kelvin. This is the main inlet, and it is at 1 meter per second, 250 Kelvin. And we have outlet with outflow condition. So this will be the symmetry plane. And we have a constant wall temperature of 600 degree Kelvin. So we go ahead and choose all of the surfaces that represent our wall. Can go to temperature, and it's going to be at 600. The most important thing here is to change the nodal output frequency. So this will write out the nodal value heat flux on the wall. On each of the nodes right here, as you can see, it will write out the surface heat flux. Click apply. Okay, so we'll go ahead and apply the material and then glove it. In order to apply the material, we can go to the assembly, choose air as the working fluid, and then we'll click update. In order to check how the solving process, we can right click on the results and view the solver log. And we can scroll down all the way. We can see that it almost converged, so we can wait for a little bit more time. And then it's done. So after it's done solving, you can see that we have two options to choose for the post-processing display. We can choose a multi-physics post-processing and the flow post-processing. At this stage, to get the heat transfer coefficient, we have to choose the flow post-processing one. So this is our post-processing window. Let's go ahead and save it, and then we move to the next step, which is exporting the results. In order to export the results in H3D format, we need to go into Accu Out. We go to Visualize, Accu Out, and then we will find the log file of our results, place where we saved it. Go ahead and open the log file. So for the output format, we want it to be in H3D, and we want to go into nodal output extended. And there's two parameters which is really important to calculate the HTC. The first one is the surface heat flux, and the second one is the temperature of the wall. So we'll go ahead and choose temperature. We hold Control and click on it, and click on the surface heat flux. So we have two parameters we want to output. And then we choose the latest time step, which is 28. For H3D option, we can either choose multi-file or single file. Me personally, I prefer single file. Process. We click Do. And then it's done writing. Go ahead and close it. For the next step is to detach the results and reattach the H3D file. In order to detach the result, we can go ahead and go to Solution Browser and click on any of the flow batteries condition. And we don't need to change it. We just click OK, and we automatically delete the results. Yes, okay. Go into the flow, the problem's name, and click Attach Results. And here we need to find the H3D file that we wrote out. And this is the H3D file. We choose MKS as our unit system. And we want to do flow post-processing. So the H3D file will contain the surface heat flux that we chose and the nodal temperature on the wall. So we click Calculate to calculate the HTC. Because this is a reference temperature that is specified by user, we need to create another variable, a new variable called tref. And in this case, I will choose arbitrarily as 333 Kelvin. But depends on the situation, the user can choose any reference temperature that they like. Click enter. For the HTC, the surface heat flux divided by the temperature difference between reference temperature and the nodal temperature on the wall. Click enter. And then we'll go to wall, drag down the menu, see the HTC variables that we just created. We put that as 50. Click display. So at this point, we have created a contour out of the HTC calculated by user specified heat flux. To recap, in this video, we have learned how to get an HTC in SimLab. The process can be broken down into 5 steps. Step 1 is to import geometry and meshing. Step 2 is to set up the simulation. The most important item in this step is to enable the derived quantity output in result request setting and enable the nodal output frequency in the wall boundary condition. Step 3 is to export the results in H2D format with the temperature and surface heat flux selected. Step 4 is to reattach the results in H3D file. And step 5 to create a calculation for HTC with user-defined reference temperature.